Afternoon, everyone. My name is Jordan Tigani. I'm a software engineer on BigQuery. I was one of the original BigQuery engineers. I've been working on it for a long time. Wrote a book about it. I'm managing part of the team now, but it hasn't been so long that I've been managing that I have forgotten how everything works. Couple of prerequisites. This is a highly technical talk. If you're not here to hear technical talk, then might not be for you. I'm not going to give any pitches or sales or marketing stuff. I'm just going to talk about technology. The only pitch you'll hear will be I'm going to try to convince you that we have some pretty cool technology in BigQuery. So the problem that I'm trying to solve with this talk is really to solve this anti-pattern that we see a lot, which is we get a customer, they start using BigQuery, everything's working great, their queries are super fast, they're happy, and then they find that they hit a roadblock. They hit something that runs slowly, it doesn't run at all, and they don't know how to fix it. And because the BigQuery architecture is so different than what they've used to, they don't have a lot of options. So they either post on Stack Overflow, they email support, or now that we're selling to enterprises, a lot of the enterprise people have the phone numbers of Google VPs, and so we get nasty emails that have to be solved really quickly. Can anybody guess which one of these is most effective in getting their problem solved? Yeah, Stack Overflow is usually gonna work. Actually, no, our support folks are really good as well, but it's nice to have like a Stack Overflow. We have a community of people that are quite helpful, and often they work for free and very helpful. So I'm going to walk through some BigQuery query plans and show you how those query plans map to the architecture. And I'm going to go into the architecture and kind of try to give you an idea of a mental model so you can develop an intuition about what's going to work, what's not going to work. This talk is called Advanced BigQuery. I'm not going to show a whole lot of Advanced BigQuery features. I'm just going to try to show how an advanced BigQuery user would use BigQuery. To start out, I'm going to review a little bit the architecture of Dremel, which is the query engine that BigQuery uses. And this picture might look a little different if you've read the Dremel paper. Things have changed in the last couple of years. It's no longer a static tree, but we have a dynamic tree that can sort of assemble different stages as needed. And I'll show a lot more of that in a minute. And then, but as always, we read from columnar store, super fast, Colossus data store, highly distributed. That's one of the keys to our success. So let's go through a simple query execution. Do a filter and an account aggregation. So how does this work? Stage one, we can apply the filter. We can do partial counts in parallel. Stage two, then we can compute the sum of those partial counts. You'll see there's some slot numbers over here. I'll describe what those mean and where we get them in a second. So this is what the query plan looks like for that query, and you can find this in the BigQuery UI. I'll show you in a couple minutes. You can see the query plan from your queries, but there's a lot of information here. So I'm going to go over it relatively slowly, so it makes it clear. So here we have basically which part of the query is running at each stage. They may look a little different than the query text that you wrote, because this is what it looks like to our query engine. So here we're reading from the underlying table, and we're applying the filter. And actually, for this kind of filter, we can actually push that into the storage layer to get a much faster query performance. But then we're also doing the aggregation of the count star at this level, and writing that to the next stage. So at the next stage, we read from the previous stage output. We compute the sum of the partial counts, and we return the total sum. Then there's these 4 timing windows here. The first one is wait. And the wait time in this one is not particularly large because we didn't actually have to wait for anything. One thing to note is that this only starts when that stage starts running. So you can see in the second stage, the stage 2 started running at the same time stage 1 did, because as soon as it gets partial output, it can start aggregating the results. In general, these have 3 different colors, or 3 different gradations. There's kind of the faintest one, which means didn't really do anything. There's the darkest one, which is the average time, and then there's the little less dark one, which is the max time. So since we're running these things in parallel, we have lots of parallel workers. This is sort of how we represent the parallelism. In this case, read didn't do much. This is reading from I/O, or this was not a significant bottleneck. The compute stage is a little more interesting here. The compute stage, the average time is actually where we spent most of the time, and the max time wasn't much higher. So this is actually a pretty healthy query, or a pretty healthy pattern, because we didn't have a lot of long tail effects. And writes was fairly minimal. Blah, blah. Okay, so the next bit of information that we have is the input and output sizes. In this query, we read over 1 billion rows, and we output 220 rows. Can anybody guess what this 220 number means? So this is the available parallelism. This is actually how many parallel machines we're running, because each one of these things is doing a parallel count, and each one outputs 1 row. So we can kind of see by using these query plans how many resources BigQuery is throwing at the problem. And because the wait time is low, none of these had to wait for to be scheduled. We can actually know that this is how many resources were actually used during the query. The next stage then reads those 220 rows and outputs just the single one. So a lot of data just on one slide. Hopefully it'll make the next ones go more smoothly. If you look at if we increase the size of the tables that we're querying over, we can look at what happens to the query plan. So this is the query plan for the same query, but just running over a data set that's 10 times as large. So we can see this is 10 billion rows. It outputs 2,000 rows, and then one interesting difference here is while the compute time is still very high, the wait time has gone from almost 0 to something much higher. And what this means is that the available parallelism was higher than the schedulable parallelism, which means that we had to wait before we could actually schedule some of these. So ways you could avoid that would be buy more slots. You could run over smaller data sets, or have queries or the compute stages that execute more quickly. So if we increase by another order of magnitude to a $100 billion row data set, we can see that actually the compute time has gone down to a very small amount, and almost the whole time we're waiting for slots, because we can see here that we have 21,000 slots. Our 21,000 is our available parallelism. And these numbers get a little bit important in a second. So it's the same query execution. It just means that we have a lot more slots, and we have the introduction of this scheduler process. And this scheduler is what actually schedules different pieces of execution to run on the different shards. Okay, so some background on BigQuery slots. We get a lot of questions on slots, what they mean, how to use them, how many you need. So the slot is a single unit of scheduling. It's it's hard to say what it actually means in terms of resources, but it is some sort of physical resources. Not all slots have the same amount of resources, so some can have more RAM, some can have more CPU, more I/O, but you can sort of thinking of it as just sort of one schedulable unit of kind of parallel execution. These can be restarted by the scheduler. They can be canceled. We'll show some queries in a little bit that can be canceled. The other key thing is it does measure, it's not a measure of performance. So some people say like, well, I want more slots. How do I get more slots? Because I want my queries to run faster. Well, your queries are only going to run faster if you're exhausting the available parallelism. So you're just getting more throughput. Often that translates into faster queries, but not always. So by default, everybody gets 2,000 slots. That's the amount of parallel things you can run. Our scheduler is balances fairly between queries within a project and then between projects overall, because this is a shared multi-tenant system. Slots can be scheduled individually for each stage of a query, and I'm going to show a slot demo if I can wake my computer up. Alrighty. So this is the Wikipedia benchmark. This is the 1 billion row data set, and running this query should take about 6 seconds. Let's see how long it takes today. 6.5 seconds, and we can see that it had 220 slots. This is essentially the same thing that we saw earlier. Here's the 100 billion row query, and this takes about 20 seconds to run when we don't do anything else. And let's try running the 1 billion row query at the same time we're running the 100 billion row query. So what should happen is the 1 billion row query should still get 220 slots because we have a fair scheduler that says, if we have 2 queries running, each one gets to use half the slots. So this query should have run about as fast as it did before, and the other query should run, maybe a little bit slower than before. So this is a little bit slower, it's about 20 seconds. Now let's try running 200 billion row 100 billion row queries at the same time, and then we can throw in our little small 1 billion row query as well. Small 1 billion. So if we think about what should happen when we do this, the 1 billion row query should still get 220 slots, and then the 2 larger ones should split the difference. So they should each get about 900 slots, and they should each take about 50% longer, or about 30 seconds. Okay, this one took 25 seconds, that one took 28 seconds. So we can kind of see how the slot scheduler works in these query times, and it generally works pretty well. You can see, we spend a lot of time in wait time. Okay, can we switch back to the presentation, please? Sorry, can we switch back? There we go. Okay, so that was sort of really simple queries. What if we want to do some more interesting things? And what can we know about the BigQuery architecture from other queries? So one problem that at least initial versions of Dremel had were aggregation with high cardinality. So let's say you wanted to do an aggregation where, in this case, if there's lots of distinct values of foo. So what would happen is we would compute these sort of partial counts in parallel, and then we would push those back up to the next stage. But one problem is that we can't actually remove any information until we've seen all of it. So this sort of master node has to see in this case that even though they only get 5 from Z, that they have to keep that around until all the remaining nodes have completed, and then only finally after the lower level nodes have completed can they apply the limit. So this would often overwhelm this master node. So we don't do that anymore. We use shuffle in the middle, or in general we don't use that anymore. So if we have the same input data, we're going to apply another step which does a shuffle. And so what shuffle does is it says, okay, we're going to put all of the things that hash into this bucket over here, and pull out all the things that hash into this bucket over here. And because we have all of the A's on the one side and all of the Z's on the other side, we can sort of make logical decisions about those. We can apply the limit at this node before we then send it up to the master node. So this makes it scale a lot more nicely. So how does this look in the query plan? So here's an example using the same data set. And a couple of things to call out. So you can see the shuffle here. You can see that when we do this aggregation, we write to a shuffle by hash. So that's going to hash these into a number of different buckets. And then we can also see that this number is now much higher. This is no longer the source number of slots that we used. This is the number of shuffle sinks. So this is the number of how many places we wrote the shuffle data to. So just to go back and reiterate this, we can apply the partial group by at the first level. We do this sort of magic shuffle. We can do the remainder of the group by, sort it, and apply a limit, and finally the final sort and final limit, sort of the merge sort and limit at the master node. And this slide just shows that we can have any number of these shuffles. So in this query, we're doing we're in the inner query we're grouping by language and title. The outer query we're just grouping by language. So we need to do 2 shuffles, and that is generally no problem. So whenever stage n doesn't know how many outputs it's going to have, we generally shuffle in between. This is the one thing in the talk that I can't talk about how it works, but it is very fast, it's very magic. It is an in-memory shuffle, and which also means that there's a limited amount of memory. If you use too much, just like if you're using too much on your local machine, you start paging, and then performance starts getting terrible. So often every once in a while, we get reports of somebody who's doing a giant query. It exhausts their shuffle limit, and all of a sudden their performance goes from like being very fast to much slower. And then the shuffle quotas we have a default shuffle quota, I think of 2 terabytes, and that's sort of the actual in-memory compressed data. But that scales up for the number of reserved slots that you have. Okay, so aggregations are simple. This is all relatively straightforward. What if you want to do a join? So when you're joining 2 large data sets, we apply the same trick. We use hash and shuffle to shuffle the left table, and we shuffle the right table so that the matching keys end up in the same spot, and we can do a local join. In the query plan, this looks like this. You can see that we're reading from each side of the join. We're writing it out to the stage output and shuffling by hash. And then here we can see the join kind of keywords are join each with each. Now it used to be that if you want to do a large join, you would have to add the each keyword. Which was sort of non-standard and not great. Now we'll figure out if we need to do an each join. The alternative, okay, and just to also see what we had to shuffle a large amount of data, but in stage 3 we didn't have to read all the rows because we were doing a limit. We were able to sort of cancel the rest of the shards because we had already had read enough data and only had to read 1 million rows. So if you're doing a small join, if you have a small, you're joining a large table with a smaller table, you don't need to do this shuffle because that would be really expensive to have to move all of the data in both tables to each location. So what you can do is you call it a broadcast join, where the small table just gets essentially sent to every single node that's processing the larger table. And then we can see this in the query plan. We shuffled the left side of the table, sorry, the right side of the table, but then we coalesced it down because maybe we were reading 10 different shards and we wanted to get it into a single shard. We shuffled that down in this pad coalesce, and then we did an each with all. So all generally is a keyword that means we're doing a broadcast join. So it gets tricky when you need to know, so say we're doing a shuffle or we're doing a filter. It's hard to know how many shards you're going to need in the subsequent query stages. So what we do is we guess, and then if we guess wrong, we change it. So here we see in stage 2, we started out with one shard. That shard, we needed more data, and added another shard, and we needed more data, and we added some more shards. So this is something that you'll see very commonly. We called it Auto Awesome, but Auto Awesome actually has several different flavors. This is just one of them, and you can see here. Sometimes in the query plans, you'll see these shuffle repartitions. These are essentially us just sort of realizing that we have to add more shards. So something that people run into as a problem sometimes is called a skewed join. Now, skewed join is when one of the keys that you're joining against has a very large amount of data, and it generally also only happens when you have sort of a high cardinality key that also has, a single one of those keys has a large proportion of your data. So sometimes we see this when somebody's doing a join on, let's say it's product ID, but half of their product IDs are the empty string, so that they might have 1 million product IDs, and that's what they really want to join on. But when they do this join, this sort of empty string makes it more difficult to schedule. I'll show why in a second. But so I'm going to simulate this by running a query where I just replace every time the title has a C in it, I replace it with just the string C. So this will be essentially half of the data set. And so this is what the query plan ends up looking like. So it still runs. In general, it still runs. But it takes a lot longer. I think this might have taken 20 minutes. And what you can see here is this compute time is all the maximum time. So this is all the long tail. So we don't even see the medium shard times. All we see are sort of the max shard times, and that's one key to know that you're seeing some sort of long tail or skew effect. To just sort of show what this looks like on the architecture diagram, we have this one shard is getting a large amount of data from one side, and this shard basically just has to churn through all of this data. It has to do a lot more work than the other shards. And we can't just apply the same sort of redispatch trick that we did for the aggregations, because we need to then reshuffle both sides. So this is something that is slow right now. It's probable that we will fix it in the future, but in case you run into this, it's a good thing to know about. Another problem that people hit a lot is they do a large order by, and they hit a resources exceeded error. So what actually happens here? So let's sort of walk through an example. As we're doing an order by foo, we have a lot of distinct values, or a lot of values that are read in parallel. But in order to sort those, the master node has to process. Somebody has to process all of these things in order to do this sort. And you can overload the master node, and you can also run out of memory if there are too many things. So here's an example of a query plan that actually hit this. Recently we added support for returning query plans even when queries fail. This can help you diagnose this kind of problem. But here you see stage two failed with resources seeded, so you can kind of see, and it failed on the sort. So that's a good indicator that that's what's going on. So what do you do when this happens? Well, you can add a limit. So in general, if you're sorting a large amount of data, you don't really care about what happens in row 1 million to 1, you just you end up running that query because that was sort of the easy thing. Which usually people tend to care about are the things at the top or the things at the bottom. So in general, you can just add a limit, and this makes execution much easier because we can do the partial sorts at the lower levels, and we can drop all of the ones that exceed the limit. And so here we can see why this is easier. And this is what the query plan for this looks like. One interesting thing to see is this output number, this 220,000. Does anybody have an idea what this 220,000 represents? So we saw that there were 220 was the available parallelism for this table. And so the limit is 1,000. So basically each one of these shards is producing 1,000 rows and sending those to the next level. And this query probably ran very fast. Just to sort of sum up some of these resource exceeded problems that you might run into, there are cases where BigQuery fails, and it probably should fail. So if you're unintentionally trying to generate too much data, let's say you're using a string ag, which basically takes will concatenate a giant string with all of the values that you're aggregating. Now, if you're doing that with 1 billion different values, you're trying to create a single string that's going to be a terabyte long. We're gonna fail. Also, if you're doing analytic functions, which are window functions, and you're not using, and you forget to use a partition by, or you're trying to sort of do this sort of a massive amount of data, that also can cause problems. Cross join is also a killer. If you have 2 million row tables and you do a cross join of those, you now have a quadrillion row table. A trillion row table, but it's easy to generate sort of massive amounts of intermediate data with a cross join, and those often will fail. So the solution to these is just sort of fix your queries to not do that. And then there's also cases where you probably don't really need the results, which is the order by, and to fix that you can add a limit. And then there's the cases where you overload a shard, like the skewed join that I showed. And the solution is to split up your queries, and this is sort of tricky, but you can basically partition your query into 2 pieces. One is you run the high cardinality part and filter out the one that is overloaded, and the second one you run just on that one, and that should be a much faster query. And then you have to combine the results. It's not pleasant, but it works. So now a little bit of a digression on how to count things in BigQuery. So there's really 3 different ways to count things in BigQuery. One is you can sort of use a group by to come up with the count. This is kind of a pain to write in queries. It's also if you're trying to count multiple distinct things at the same time, it can be really difficult to write the queries. But it's an exact and reasonably scalable way to do it. The other way is count distinct. One of the things that people hated about the BigQuery legacy SQL was that count distinct was approximate by default, and we have since fixed that in BigQuery standard SQL. We have quite a nice implementation of count distinct, but it is going to be reasonably slow because I'll show in a second why counting distinct values is hard. And third, we have approximate count distinct, which is very fast, but it is an approximation. This is sort of a new implementation that we've just added that uses an algorithm called HyperLogLog++. So HyperLogLog++ uses HyperLogLog, which is an algorithm for doing cardinality estimation. And HyperLogLog++ is just sort of Google's version of that kind of applies using a lot of experience in using this, and it tweaks it a bit. It has better estimations at certain cardinality ranges, better accuracy, and uses less memory and is faster. In general, you don't have to know that that's what's being used under the covers. You just get accurate count distinct answers. So these are some benchmarks that I ran against our data set of various sizes, and we can see that the error is staying under 1%, but the performance is much faster. And these are log lines, so it really is much faster on large data sets. So we've also added some HyperLogLog functions that kind of give you a little more control over this. This is kind of geeky, but I don't know, I find it pretty interesting. So one of the things that you might want to do is you might want to sort of count distinct users by language from the GitHub data set, where language is the programming language. So this takes looks like 23 minutes to run because you're running count distinct, but really you probably don't care about the exact values. So you can run if you use a prox count distinct, it'll run like 60 times faster, so it's 22 seconds instead. But one of the issues with when you're counting distinct values, and this doesn't, it holds whether you're using an approx count or an exact count, but if you try to take some approximate counts and then sum those up, so if we want to get the sum of distinct users per language and then find the total number of distinct users overall, those numbers can't be summed, because like some of those same users that were using Perl are also using Ruby, and it's hard to know what those are. So there are some HyperLogLog functions that let you kind of split up the process of this counting into different pieces. And the first one is it builds a sketch. A sketch is sort of the kind of a probabilistic mapping of the values and the cardinality of the values. And so you can break it up into two steps. First, you do the init, which creates the sketch. The second, you do the extract, and this actually will return the same the same value. Go back. The same value that the other approx count distinct returned. So why would you want to do this? Well, one option is sometimes you have PII data and you want to do aggregations, but sometimes if you do aggregations, then you lose kind of the distinctness. You don't know how many kind of unique users you have. So this lets you save a relatively small sketch. And then finally, you can do the extract, which computes the distinct values. And then, but the nice thing about the kind of cool thing about these sketches is you can combine the sketches. So if you do merge, you can actually compute the sum of multiple distinct of each distinct sketch. So you can come up with the total sum of all distinct users per all distinct users in GitHub. And so the overall number you get is the exact same number as if you'd done the number of prox count distinct. I'm just sort of summarize these. That you can use these to anonymize user IDs. You can use these. So there's sort of multiple HLL functions. We should be releasing documentation on those shortly. Okay, so I'm going to go to another demo, And so now that I've shown like how to do this in general, let's kind of walk through a query that is slow and show how we would actually optimize it in practice. If I can type my password in. Okay. Okay, so for this one, I'm going to use one of my favorite tables here, and this is this is our petabyte data set that we built for GCP Next last year. So this table is 1.1 petabytes. It's 1 trillion rows. It's part of sort of this retail data set that kind of looks like a retail schema that you might be used to seeing. We applied some kind of advanced BigQuery techniques to this that are best practices. So here, instead of having a sales table and a line item table, we basically denormalize that into a single row that has the sale and the line item as sort of a nested value. So you can see how we have this here. We have the sale, and then we have each of the line items within that row. But there's still 1 trillion outer entries. So the inner entries are probably something on the order of 10 to 20 trillion. Okay, so here's the query that I want to run. Hopefully that's a little bit legible. But I want to show that, like, yeah, you can do complex queries, and you can over data of this size. So one of the things techniques we're doing here is we're looking at since this table is partitioned, we're going to do a partition filter. So we're going to just do 1 month of data. We're also using a window function, so we're doing a partition and order by to compute the running average of sales for each product. And let's see. We are also, we're doing a join. So we're joining from this giant table to our products table. And I didn't want to make you guys wait while I ran this query, but I ran it right before, and it took 2 minutes. Now, one interesting thing here is it only processed 1.8, or almost only processed 2 terabytes. So there's a couple of reasons for that, even though it's a petabyte table. One is we only bill you for the columns that you read, so we only read a few of the columns. And second is we only bill you for the partitions that you read, so we only needed to read the sort of 1 month's worth of partitions. But there was still a lot of data here, and we did run a regular expression over a lot of data. So here's what the query plan looks like. So what do we see from this query plan? So we see that stage 1 is actually where we spent almost all of our time, and we notice that the output rows were larger than the input rows, and so that seems a little bit funny. But one of the things that we had to do here in this query is we ended up flattening these line items. So for each of the line items had to be unnested. And so this is where we spend a lot of time. Now these look like repartition stages, and if you look at that, then yes, that's what they are. This other one, so it looks like this stage that processed 10 billion rows, that's an interesting one. So we look in here, and we can see that we didn't each all join. So we did a broadcast join. So that's positive news. We know that we didn't have to shuffle. We didn't have to shuffle actually these 10 billion rows because that would have been expensive. Or did we? Actually, we did. So actually, that was expensive. But so what do we like? let's look at the stage where we read. So this is the stage where we read the products table. And so the products table had 2 million products, and we filtered it down to 600 projects, which is why we could do the broadcast. But actually, it only started out as 2 million products. So one of the things we could do is, so we're applying this filter here. We're filtering on the, and there's actually one nice thing in standard SQL is we actually have an optimizer. We can push this filter inside the inside the join. But we're filtering on the key while it's in products. If we change this to filter the key while it's in the sales table, we'll end up having, we can push this all the way into the storage layer. We can end up having to read out a lot less data, and hopefully this query should go faster. So let's see how long this takes. Come on, BigQuery. So 30 seconds. So that's a lot faster, factor of 6, to give us the same answer. Now notice one other option we could have had was we could have run it on a smaller set of partitions, but we want to do the trailing weekly average, and so if you do it a lot less than a month, then that's going to you may not get the type of answers that you want. So here we see that the big difference is in this first stage, where we still had to read the underlying 7 billion rows, but we only had to output 4 billion. And we can see that this filter, this regular expression, was pushed down into this layer here. And can we switch back to the presentation? Okay, so that's all I have. There's some other, if you like BigQuery, there's some other presentations you might be interested in. There was a data model. Obviously these have already passed, but they will be online so that you can stream them at your leisure. But thank you.